Alright everyone, so I think we're up and running. So as I said before, everything has gone online, so I guess we're going to have to try something a little bit differently. So what I figure we'll do is I'll go and narrate just videos similar to what we would do in class, and we can do that on kind of a trial basis, see how it works, and then go from there. So what I figure is I have 10 topics left, including what we didn't get through last time on Wednesday. So I'll finish that up and then do a couple more. Nicely, I have 10 topics left that I'd like to do. We've already done 5 quizzes, so 10 seems like a nice number. So what we can do is break the 10 topics into 2 topic subgroups and then do quizzes on each of the 5 groupings to remain. Okay, so we were talking about plotting functions. So what we'd said is that we have nice functions that kind of look like this, and what we'd like to be able to do is to be able to more or less draw these by hand. So what we want to do is take advantage of various properties from the function and also the derivatives so that we can tease out some nice properties in the functions to go and plot them all out. So some of the things that we want to look at. So we want to look at symmetry, intercepts, asymptotes, and then various properties of the derivatives. So critical points, inflection points, increasing, decreasing, and also concavity. So the first of these things is symmetry. So if you give me some function f, we'll say that it has even symmetry if f of x is f of minus x, and odd symmetry if f of x is minus f of minus x. So what this means, practically speaking, is that for a function with odd symmetry, you can take the positive part, rotate it around the origin by 180 degrees, and you have the negative part. So for example here, if we go and we split things with the positive side, if we took everything on the positive side of the x-axis, we rotate it around the origin by 180 degrees, we'd get the negative side. So in general what we see is that for every x value and y and corresponding y value, we'd get that we have the negative x value, negative corresponding y value. So for this, so an example of this kind of a function would be something like sine of x. And as I mentioned before, we could go and write sine of x as just an infinitely long polynomial, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. And then if we're looking for even symmetry, what we're looking at is something where we could take a function and the positive side is the mirror image of the negative side. So if we went and just folded the function over on itself, folding it down the y-axis, we'd get the exact same thing. And what we have is that for every positive x value and corresponding y value, if we go over to the negative x value, we get the same y value. So an example of this would be something like cosine, which we could write out as 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and so on. Now the terminology of even and odd symmetry isn't a coincidence, because what we see here is that we have an even function in cosine, and in the writing out of the polynomial, all of the terms of x that we see have even powers of x. 1 we could write as x to the 0. So we just have even powers of x. For a function with odd symmetry, we just see odd powers of x, and in general that's what even and odd symmetry means. So if you have a function that has even symmetry, assuming you have a polynomial or a rational function or something, you'd have only even powers of x. An odd function, so an odd polynomial, odd rational function, something like that, you'd have only odd powers of x appearing. Now, it's possible that you have neither. So for example, suppose we had sine plus cosine, we'd have a mixture of even and odd terms, and we wind up with neither even nor odd symmetry. Okay, we could also go and remember what we said back in January or February about asymptotes. So we had vertical asymptotes, which were places where the denominator was going to go to 0, either from the positive side or the negative side, while the numerator went to some non-zero number. So in this case, something like 1 over x squared, we'd have a vertical asymptote at x equals 0. And then we also had horizontal asymptotes, so remember those were where we would take limits as x went to plus and minus infinity. And we said that if our limit as x went to plus or minus infinity went to some fixed number, we'd have a horizontal asymptote at that corresponding number. Briefly, we can also talk about what are called slant asymptotes. So slant asymptotes are somewhat similar to horizontal asymptotes with a slight twist. So with a horizontal asymptote, what's happening is that as x goes to plus or minus infinity, your function is going towards some number. Here with a slant asymptote, what's happening is as x goes towards plus or minus infinity, the function is going towards a line. Or another way that we could express it is that the difference between the function and some line y equals ax plus b goes to 0 as x goes to plus or minus infinity. And we could say exactly the same kind of thing with horizontal asymptotes. So if we'd said that a limit as x goes to infinity of f of x equals some number m, we could say that the difference between f of x and m goes to 0 as x goes to plus or minus infinity. So for example, with this case, which we have pictured here, so x squared plus 1 all over x, we could rewrite our function as x plus 1 over x. Well, if we take the line y equals x and subtract it away from our function f, we're just left with 1 over x, and as x goes to plus or minus infinity, that expression will go to 0. So the difference between the function x squared plus 1 all over x and the line y equals x goes to 0 as x goes to plus or minus infinity, and as pictured, we'd say that the line y equals x is a slant asymptote for this function. Okay, so in general what we want to do is we want to go and take our function, take the derivative, take the second derivative, and factor them as much as we can, and then pick out some properties from the function, the derivative, and the second derivative. So with the function, we want to find where the function is actually defined. We'd like to find any vertical or horizontal or maybe slant asymptotes. Maybe we could find if the function has even or odd symmetry, and then any intercepts. So places where the function crosses the y-axis and also where the function crosses the x-axis, or places where the function evaluates to 0. From the first derivative, we'll go and find critical points and then any local maximums or minimums, and also where the function is going to be increasing and decreasing, and then similarly for the second derivative, we'll find inflection points in places where our function's either going to be concave up or concave down, and we'll use charts as we've done so far. Okay, so let's go and do two examples. So we'll do x squared plus 2x plus 4 all over 2x, and then we'll do x squared minus 1 over x squared minus 4. Okay, so first example. So we have x squared plus 2x plus 4 all divided by 2x. What we can see is that our function is a rational function, so it's going to be defined and also continuous everywhere where the denominator is non-zero. And we see that the denominator is only going to be 0 at x equals 0. So the function will be defined everywhere else. For symmetry, we could go and rewrite our function as x over 2 plus 1 plus 2 over x. What we see is that we have a mixture of even and odd powers of x. So we have x over 2, so we have a term with an odd power of x. We have 2 over x, or 2 times x to the minus 1. Minus 1 is also an odd number, so we have another term that has an odd power of x, but 1 is just 1 times x to the 0. X to the 0 is going to give us an even power of x. So this mixture of even and odd terms, or even and odd powers of x, tells us we're not going to have even or odd symmetry, so we have neither. For asymptotes, we said that our function is going to be undefined at x equals 0, and that's because the function is going off to infinity at x equals 0. And from what we just wrote above, what we'd see is that if we take away the line y equals x over 2 plus 1, the difference between f and that line is going to be 2 over x, and as x goes towards plus or minus infinity, the difference between f and the line x over 2 plus 1 is going to 0. So that line will be a slant asymptote for this function. And lastly, we have no intercepts. So there's no place where f of x is going to evaluate to 0, and the function doesn't cross the x-axis because, as we'd said, the function is not actually defined at x equals 0. Okay, so from this, the first things that we can take away are that we have this dashed red line, which will give us our slant asymptote, and it's probably very hard to see on this, but we're going to have a vertical asymptote at x equals 0. Okay, so the next thing that we could do is we could go and look at the limits about what's happening around x equals 0 to just figure out whether or not our limits are going off to plus or minus infinity at 0. So if we look at the right side limit, the x over 2 and the 1 part aren't going to be that interesting, but the 2 over x is what's going to be going off to infinity. And what we see there is that as x goes to 0 from the right, 2 over x is going to give us some positive expression where the denominator is going to 0, so that limit will evaluate to plus infinity. Then as we take the limit as we come at 0 from the left, our 2 over x term will give us something negative where our denominator is going to 0 and the numerator is clearly fixed at 2, so that limit will go off to minus infinity. So we can put these data points into the plot. Okay, so we can see from the plot that our function is going towards plus infinity as we come to 0 from the right, minus infinity as we go to 0 from the left. Okay, so what else can we do? Well, we can go and take our two derivatives. So we can easily find that f prime we could write as, after some factoring, x minus 2 times x plus 2, all divided by 2x squared, and our second derivative is going to be 4x cubed. So we'd now like to just go and make a table to tell us what's happening with the first derivative. So again, remember that on the column, we're going to go and put the factors for f prime that can change sign on us. The 2x squared, it's always going to be positive, except at 0, where it's going to be 0, but we're not really going to concern ourselves with that point because the function's not defined there. So 2x squared, always positive, so we don't need to concern ourselves with it. And we have our x minus 2 and our x plus 2 factors, those could change signs on us. So we're going to need to concern ourselves with them. For critical points, places where the derivative is either 0 or doesn't exist, the only ones there are going to be x equals 2 and x equals minus 2. So we'll go and split the real line up to consider x values to the left of minus 2, x values in between minus 2 and 2, and then x values bigger than 2. So for the x minus 2 factor, if you take an x value that's to the left of minus 2, such as minus 3, you'll get a negative value. If you take an x value in between minus 2 and 2, you'll get a negative value. But if you take an x value bigger than 2, such as 3, you get something positive. For x plus 2, when we take a value that's to the left of minus 2, we'll get something negative. But for something in between minus 2 and 2, we get something positive. For an x value bigger than 2, we'll also get something positive. So when multiplying all of the signs together, this tells us that f prime is going to be positive for x values to the left of minus 2, so f will be increasing there. In between minus 2 and 2, f prime will be negative, so f will be decreasing. And then lastly, for x values to the right of 2, f prime will be positive, and f is increasing. Okay, and then the last thing that we want to consider is f double prime. So what we have is 4x cubed for our second derivative, something very easy to look at. The only factor that we have showing up here is the x cubed. And the only place where this could possibly flip signs on us is going to be at 0. So if you give me any negative value, our second derivative will be negative, so f is going to be concave down. And if you pick any positive value, f double prime is going to be positive, so f is concave up. Okay, so then what this says is that we're going to get an inflection point at x equals 0, and then we could go back to our table from our first derivative to go and pick out critical points, or pick out local maximums and minimums. So we'd said that 2 and minus 2 were going to be critical points for our function, and what we see from our first derivative test is that as we approach minus 2, the function is increasing. We hit minus 2 and then start decreasing, so minus 2 is going to be a local maximum. And then at x equals 2, our function is going to be decreasing, hit x equals 2, and then start increasing. So we'll have a local minimum at x equals 2. And when we put all of this together, what we wind up is this plot. So what we would see is that x equals -2, it's a local minimum or a local maximum, increasing to the left at -2, and then we start decreasing. Similarly at 2, our function is decreasing, hits 2, and then starts increasing from there. And then we also have the concavity as we would like. So our function is concave up on the positive values, concave down on the negative values. Okay, so that takes care of everything that we need to say about this one. So for our second example, so x squared minus 1 all divided by x squared minus 4, we can see that our function is defined everywhere so long as x is not plus or minus 2. For symmetry, we have a rational function where the numerator is going to be an even function, the denominator is also an even function, and when we divide those two, we'll keep an even function. So for something like this, it works very much like subtraction. So if you subtract an even number from an even number, you get an even number in return. So here we have an even number divided by an even number, we get even symmetry. For asymptotes, well, what we would see is that at x equals plus or minus 2, our denominator is 0, our numerator is something non-zero, so we'll have vertical asymptotes at plus or minus 2. And we can see we have horizontal asymptotes at y equals 1. So again, remember we have a rational function. As we take our limits towards plus or minus infinity, we just need to consider the ratio of biggest terms. Our biggest term in the numerator and denominator is both x squared. Their ratio is 1. So we'll get y equals 1 for horizontal asymptotes. And then lastly, intercepts. So we'll get that the function will cross the y-axis at x equals 0, y equals 1/4. And then the function will evaluate to 0 at plus or minus 1. So places where the numerator is 0, denominator is non-zero. Okay, so we could start off by just taking advantage of this. So we'll have our dashed vertical line to denote the asymptotes, and we'll have our dashed horizontal line to denote the horizontal asymptote. And then we have the 3 points that we'd set, so the 3 intercepts. 2 places where the function evaluates to 0, and the point where the function crosses the y-axis. As before, we'd like to go and see what's happening around our vertical asymptotes. So we just want to look at the one-side limits around plus or minus 2. At this point, I think we know how to do that. So we can just kind of gloss over how we got all of this. For x going to 2 from the right, we'll have x plus 1 will be going towards 3. X minus 1 will be going towards 1. X plus 2 will be going towards 4. X minus 2 will be going towards 0. But x will be coming at 2 from the right, so x minus 2 will be positive, so we'll have a positive times a positive, divided by a positive, and divided by another positive, so everything is going to be positive here. Denominator is going to 0, numerator is going towards 3, so we'll wind up with plus infinity. And we could do the same kind of analysis with signs to get minus infinity, and plus infinity. So if we put all of those onto the plot, what we see is a sign that looks like this so far. And then we'd like to go and keep doing the same kind of thing that we just did before. So we could go and find our first and second derivatives with a little bit of effort, and then we want to go make our table. So what we'd see here is that f prime of minus 6x all divided by x squared minus 4 with that denominator squared. The denominator is not going to change signs on us. So long as it's not 0, it's going to be something positive because we're taking a quantity and squaring it. So the only quantity that we need to look at for our column is just going to be the numerator of minus 6x. Well, clearly what we see is that we're going to have a critical point of 0. That's where the derivative is going to be 0. And the 2 places where the derivative is undefined are places where the function itself is not defined. So only critical points going to be x equals 0. So if you give me any negative value, minus 6x will be positive, so our derivative is positive and our function is increasing. If you give some positive value, minus 6x is negative, f prime is negative, f is decreasing. So the first thing that this says is that x equals 0 is going to give us a local maximum. So increasing to the left of 0, we hit 0 and start decreasing. So we have a local maximum. For our second derivative, what we would see is that 3x squared plus 4 is always going to be something positive, so we don't need to concern ourselves with it when we go and try and figure out all the signs. But we do need to concern ourselves with x minus 2 cubed and x plus 2 cubed because those two factors could switch signs. So what we'd see is that these factors are going to be 0 at plus or minus 2, so we just want to consider what's going on each side of these values. So split the x-axis up again, x values to the left of 2, x values in between minus 2 and 2, and then x values bigger than 2. So for an x value to the left of 2, x minus 2 will give you something negative. You're then going to cube a negative value, get a negative value in return. The same is going to hold true for x plus 2 cubed. You'll take something like minus 3, add 2 to it, get something that's still negative and cube the negative value, wind up with a negative value. For something in between minus 2 and 2, such as 0, you take 0 minus 2, you get something negative and cube it, again, we get a negative value. But we take a value in between minus 2 and 2, add 2 to that, we'll get something bigger than 0, so we wind up with something positive, and we cube that, we clearly get a positive. And then lastly, for x values bigger than 2, we'll get positive values out of x minus 2 cubed and x plus 2 cubed. So when we go and we multiply out all of our signs, we'll see that f double prime will be positive for x values to the left of minus 2 and to the right of 2, but negative in between minus 2 and 2. So f will be concave up to the left of minus 2 and to the right of plus 2, but concave down in between minus 2 and 2. So then if we put all of this together, we wind up with this very nice plot, and we get everything that we would like. So our function is increasing on all of the negatives. The one thing you could note is that we kind of cheat around the place of discontinuity, but outside of that point of discontinuity, the function is always increasing over on the negative side, and then the function is always decreasing over on the positive side, again, kind of ignoring where we're cheating here around the point of discontinuity. And then what we see is that, again, yes, the function is concave up to the left of minus 2 and to the right of plus 2, concave down in between minus 2 and 2, and we get that local maximum at x equals 0. Okay, so I think that covers about everything that I need to say about plotting of functions. If you have any questions about anything that we've said here, please don't hesitate to email me. Yeah, so I think that's about all.